Hello, it's Mrs. Avon again. Today we're going to look at section 3 in chapter 4, titled Interaction Forces. In the first part of the chapter, we defined a force, which is just a push or a pull, and then we looked at how forces behave with Newton's first and second laws. Remember, the first law is inertia, and the second law is F net equals m times a, mass times acceleration. What we're going to look at today is the third law, which is typically referred to as action-reaction. And if we state it formally, it says for every action there is an equal and opposite reaction. If we want to state it as a mathematical equation, the force of 1 on 2 is equal to the force of 2 on 1, but we have to put the negative in there because they are equal and opposite. Because we know from Newton's second law that F equals ma, I can rewrite that as m1a1 equals m2a2. So before we start using that equation, we're going to look at how we identify action-reaction pairs. If I have a baseball hitting a bat, the baseball forces the bat to the left in this picture, and the bat forces the ball to the right. So when I'm describing the interaction pair, I simply take the two nouns, baseball and bat, and I switch them. When I look at interaction pairs, it's very important to note that they are acting on two different objects. The baseball acts on the bat, and the bat acts on the baseball. So if we take a picture of a person being pulled by an elephant and a tractor, I can identify at least 6 interaction pairs. So the first interaction pair would be the elephant's feet on the ground and the ground on the elephant's feet. I have another one, the elephant on the rope on the elephant. The boy on the rope on the boy. And I would have the same thing on the other side. Boy and rope and tractor, and wheels and ground. Okay? I also have the boy to the earth and the earth to the boy because I have gravity in every situation. Again, it's very important to note that when we draw a free body diagram, we are only drawing half of the action-reaction pair. So I have the boy who's being pulled to the right by the first rope, Ft is just tension. He's being pulled to the left by the second rope, so Ft2. His weight, or the force of gravity, which sometimes we write here Fg. Either one is fine, our book uses Fg. And then because he's standing on a surface, a little hill, we have a normal force. So that only shows you half of the action-reaction pair, and it shows you only the forces that act on the boy, not his reactions. So if we want to look at Newton's third law in mathematical terms, we take an example out of your textbook, example problem 3. When a softball with a mass of 0.18 kilograms is dropped, so I have the ball, the mass is 0.18 kilograms. Its acceleration towards the earth is equal to g. So I know that a is equal to 9.8 meters per second squared. The acceleration due to gravity, and I know that that's negative. What is the force on earth due to the ball? What is the earth's resulting acceleration? So if I want the force of 1 on 2, I simply take the mass times the acceleration. So I'm going to plug into my calculator 0.18 times 9.8, which is 1.764, but I only need 2 significant figures, so that is 1.8 newtons. According to Newton's second law, the force of third law, 1 on 2 is equal to the negative of the force 2 on 1. Okay. This is a negative because I use a negative 9.8. So that means the force of 2 on 1 is also equal to 1.8 newtons. Then it asks, what is the force on Earth and what is the Earth's resulting acceleration? So if F2 on 1 is equal to m2a2, I know that m2, it tells me in the problem, is 6.0 times 10 to the 24th kilograms. So all I have to do is rearrange it for A2. So that's going to be F 2 on 1, which I know is 1.8 newtons, and I'm going to divide that by m2. So I take 1.8 newtons, I divide that by 6 exponent 24. So 1.8 divided by 6 exponent 24 in my calculator gives me that the acceleration of the Earth towards the softball is, and I need again two significant figures, 3.0 times 10 to the negative 25th meters per second squared. Notice that the acceleration of the ball being 9.8 and the acceleration of the Earth being 3.0 times 10 to the negative 25th are very different. In comparison, the acceleration of the ball is very large, but the acceleration of the Earth is very, very small, and that has to do with their masses. So, can we answer this question? How does Newton's third law affect the acceleration of objects with different mass? Consistent with Newton's third law of motion, the bullet pushes backwards on the rifle. The acceleration of the recoiling rifle is. If I look at the mass of the bullet compared to its acceleration, the mass is small, the acceleration is very large. If I look at the mass of the rifle in comparison, it's very large compared to the bullet. Therefore, because these two have to equal each other, its acceleration has to be very small. So the acceleration of the rifle, which is the right side of this equation, has to be greater than the acceleration of the bullet. No, because then they wouldn't equal. Smaller than the acceleration of the bullet. Well, that's exactly what it says. Or the same size. They cannot be the same size because then Newton's third law would not hold. Now that we can identify action-reaction pairs, that may help us also identify individual forces. When I look at the forces on ropes and strings, I call those forces tension. So it says a 50-kilogram bucket is being lifted by a rope. The rope will not break if the tension is 525 newtons or less. The bucket starts at rest, and after being lifted 3 meters, it is moving at 3 meters per second. If the acceleration is constant, is the rope in danger of breaking? So the first thing I'm going to do with any force problem is draw a free body diagram. The downward force is always going to be Fg, and anytime something is being pulled by a rope, just as we saw earlier, I call that Ft, or tension. So I know that Fg equals mg, and my mass is 50 kilograms. So I'll take 50 times 9.8, and that gives me 490 newtons. So I know that the weight, or the force due to gravity, for that bucket is 490 newtons, and it wants me to find the tension. Okay. The maximum tension is 525. If I exceed 525 newtons, my rope is going to break. So the second step after you draw your free body diagram is to sum the forces. Ft minus Fg equals ma. I know that I'm solving for Ft, so I'll rearrange. Ft equals ma plus Fg. Okay. At this point, I can't go any farther because I don't know the acceleration of the bucket. It just says it's constant. So here's where I keep saying that those motion equations aren't going to disappear. It tells me the bucket starts from rest, so I know Vi. It tells me it's lifted 3 meters. It tells me that it's moving at 3 meters per second, so that's its final velocity. And it wants me to find its acceleration. So I don't have time, so I use the fourth motion equation, and I rearrange the fourth motion equation for acceleration, which would be Vf squared minus Vi squared over 2d. So I plug into my calculator 3 squared divided by 2 times 3, which gives me 1.5. So the constant acceleration of the bucket is 1.5 meters per second squared. The commonality between Newton's second law and the motion equations is acceleration. So if you're not given the acceleration in the problem, or you're not asked to find it, then you're going to need to use a motion equation to obtain that information. And then I can simply go back to this equation and I take my answer, which is 1.5, I multiply it by the mass, which is 50, then I add to that the weight of the object, which is Fg 490. So the tension is 565 newtons. And it looks like, yes, that will break. That is above the max of 525 newtons. So when I start to analyze the problems, the first thing I need to do, and you should write down these steps, draw the free body diagram and list your knowns right on it. Okay, I could also put here that the mass is 50 kilograms. That might be helpful to write down as well, 50.0. The second step is to sum your forces. It will always be up minus down or right minus left. That is equal to mass times acceleration, because Ft minus Fg equals F net. And then I just plug into my equation and solve. So 3 steps: free body diagram with knowns, sum the forces, which would be F net equals ma, and then find the answer. Another force that we will be dealing with is called the normal force. The normal force is always perpendicular to the surface. So anytime an object is on a surface, opposing gravity, there is an upward force. So Fg is down, and then there was an upward force. We call that force the normal force. Normal means perpendicular. So if I'm at rest on a surface with no other forces acting, the normal force is equal to the weight, or Fg. If I would grab a hold of the string and pull up, if I were to sum the forces, I would have Fn plus Ft, because I'm pulling up on the string, so that's tension, minus Fg equals ma. Even if I don't lift it, if I just pull up slightly, Fn becomes Fg minus Ft. So if I'm pulling up, the normal force is going to be less than the weight. If I'm pushing down, it will be Fn minus Fg minus F, let's call it P for the push, equals ma. It's not going anywhere, I'm just pushing on it. So the normal force will be Fg plus Fp for push. So the normal force can change depending on whether the object has additional forces acting on it. If it does not have additional vertical forces acting on it, the normal force will be equal to gravity. And we will work more with this in Chapter 6.